Having me. I'm really excited to be able to talk to you about InSight and some of the things we found in the first couple of months on Mars. Just to let you know how this presentation will go, I want to put InSight in the context of past and potential future planetary missions with the geophysical focus. So to do that, I'll set up how terrestrial seismology has really helped our Earth science perspective and what we know about the Earth, and then how it led to more planetary missions. The main part I'll be talking about InSight and specifically its seismometer, as this is an IRIS presentation. And then I'll talk about some other potential seismometers out in the solar system. So as many of you might know, if you have a seismic background, seismology has been really critical for the understanding of what's going on in our Earth. Some of the really big picture contributions have been internal structure. So on the left, you see from Shearer's book, the internal structure based on the PREM model. So this is the preliminary reference Earth model. This would be sort of a gold standard for any seismometer to be able to constrain what's going on beneath it. So the big scale, mantle, core, crust, transition zones, that sort of image of the internal structure of the Earth. So earthquakes and seismology have really played a crucial part in figuring out what is going on inside the Earth. And it's also led to the plate tectonics theory. So as you see on the image on the right, earthquakes tend to cluster around plate boundaries. And this signature, as far as we know, is really unique to the Earth. Other planets tend to have stagnant lids or one lid, so they may not have this feature where the earthquakes tend to line up. But this is one of the things we plan to look for as we go and explore other planets. You'll also notice on this map, because it's color coordinated for depth, you can see where plates are subducting underneath one another. This is another signature that might be unique to Earth. Of course, seismology, in addition to providing really crucial science, has been really important for the general public. Anyone living in earthquake country, California, Alaska, other places around the world, your building codes might be based on our understanding of local seismicity. This is also something we might bring to planets as we move forward with exploration. As far as we know, Earth is one of the more seismically active places, but we do want to take that into account if we want to build permanent structures. And then, of course, seismology has also been used for industry and commercial use. In particular, the oil and gas industry uses seismology to image the local substructure to look for reservoirs. This, believe it or not, could also be used in the planetary setting as we move forward with in situ resource utilization. So we might be able to use things like GPR or seismic lines to see if there's resources that lie beneath the planetary surfaces. In particular, on the moon, we might look for traps of liquid, or not liquid water, but ices and things that we could use for maybe rocket fuel or resources for those permanent habitable structures. So because terrestrial seismology has yielded such critical information, it makes sense that as we move out, we want to bring seismometers with us. So the first seismometer beyond Earth was the Apollo 11 seismometer that landed in 1969. So not only is it the 50 years of the Apollo missions landing on the moon, but it's also 50 years of planetary seismology in a sense. So these seismometers were really important because they show that they can work outside of Earth. Apollo 11 seismometer lasted about 3 weeks or so, which was pretty long. It lasted a full lunar night and into a day before it overheated, but it paved the way for future seismometers on the moon. So 12, 14, 15, and 16 brought along seismometers, and they were able to build the first lunar network of seismometers. With these, they had active sources, so they had explosives, and this allowed them to know the precise location of the events. And then there were also some passive recordings of naturally occurring moonquakes. So on Earth, we have earthquakes, but once we start measuring them outside of Earth, the name changes. So if you're on the moon, they become moonquakes. If you're on Mars, they become Marsquakes. So as I mentioned, there were some important findings from lunar seismology. This image is taken from the Weber et al. Science paper in 2011, and it shows a couple of important aspects. First thing that I want to point out is if you look at panel B, it labels where the longer lasting stations were. So that's where 12, 14, 15, and 16 are. And what you'll notice is they all are on the near side of the moon, so they face Earth, and they're all pretty close to the lunar equator. This was for a number of reasons. One is that seismology was not the primary focus of the Apollo missions, so there wasn't necessarily this desire to spread them out equal distance from each other. But because they are clustered together, we have a better sense of what's going on within the moon on the near side, and the far side remains a bit of a mystery. So this is one thing I'll talk about much later in the talk for future investigations using planetary seismology. So while the Apollo seismometers were recording, the most common event that they recorded were deep moonquakes. These tended to occur in clusters. So if you look at panel C, you'll see 3 individual seismograms from the A6 cluster, and then what they look like when you stack all 53 of those events on top of one another. In addition to the deep moonquakes, there were also some shallow quakes, but they were a bit more rare. So these were either small local thermal events from the lunar surface heating up and then cooling, and there were also contractional events. So about a year ago, or maybe earlier this year actually, there was a paper that came out that showed that the moon is shrinking, and as it shrinks, it generates seismic events. So these are the sort of contractional events I'm talking about. There's also meteorite impacts. So anyone that's ever looked at the moon notices that there's a lot of large craters, and as these impacts occur, they're going to generate seismic signals. A key finding from these naturally occurring events and also the active source events was that there's significant scattering. So if you were to look at these stacked events, you'll notice that even though there's 53 of them, it's still a bit noisy, and it can be somewhat difficult to identify P and S waves. That's because the moon has a thick megaregolith, and it creates diffusive scattering. So instead of having a sharp arrival like you do on Earth, you end up with more of a coda. And this makes interpreting the seismic signals a bit more difficult. It's not impossible. So we have been able to constrain the crustal thickness of the moon, determine that there could be this partial melt layer, and that the moon in fact does have a core. But again, this is something that as we move forward with planetary seismology, this is one of the effects that we need to think about. All in all, though, the Apollo experiment was very successful, and it led to putting seismometers other places. So back in the late 70s up until 1980, there were the Viking missions. So Viking 1 and Viking 2 both had seismometers. The seismometer is essentially in the center of your screen. It's the small square-ish looking box. The Viking 1 seismometer didn't uncage itself correctly, so it didn't record very useful data. However, Viking 2 did uncage properly. These seismometers, much like Apollo, were tasked with constraining the Martian seismicity, and they were also looking at the internal structure. So they wanted to figure out the prem for Mars, and they also wanted to see, is there a signature of plate tectonics, or where does the seismic activity tend to cluster, things like that. The seismometer was built so that it could measure the lowest Earth noise that we have on Earth. So if you're familiar with the new low noise model, it's in that range, and I'll discuss that a bit later. However, you'll notice that the seismometer is actually sitting on the deck of the lander. So unlike InSight, it was never placed on the ground. Because it's on the lander and it's not protected, the main source of noise was wind. So in addition to the seismometer, Viking did carry other instruments, including a pressure sensor and a temperature sensor. So using those two instruments, they were able to correlate wind noise with the seismic signals. However, there was one possible Marsquake. And I say possible because it happened when the pressure sensor happened to not be working. So we can't 100% rule out that it was wind. That's why there's still a little bit of a debate over whether or not it actually recorded a Marsquake. And that brings me to InSight. So a lot of people will say InSight is the first seismometer on Mars. And if you're talking about being on the surface of Mars, that is absolutely true, but Viking is technically the first seismometer to visit the red planet. It just never touched the ground. But InSight stands for the Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport, and I'll be mostly focusing on the seismic investigations. InSight was part of the Discovery class program. So if you're not 100% familiar with how NASA funds missions, there's different tiers based on the budget of the different missions. And NASA along with the planetary community, tends to decide targets that it might like to visit in the different programs. So Discovery tends to be a lower cost mission. And by lower cost, I mean it tends to be capped around $150 million or so. When InSight was initially submitted, it was referred to as the Geophysical Monitoring Station, and that because it is really its first of a kind mission in that it is a geophysical observatory. So unlike previous missions to Mars, which tend to focus on finding water or looking for life, InSight is really tasked with looking at bigger picture and looking at the geophysics of Mars, and that's what really makes it different. So the main science questions InSight looks to answer is, how did the terrestrial planets form and why did they differ in terms of their evolution? So here I'm showing the different terrestrial planets and including the moon in there as well. So one of the things you might notice is they have different core sizes. So Mercury, we know from moment of inertia constraints and density constraints that its core is relatively big compared to the planet as a whole. Venus is Earth's twin, and we're still not 100% sure why it's evolved to be so much different on the surface than Earth. But maybe one of the answers could lie with internal structure, and that's partially where Mars also comes in. So Mars, its radius is half the size of Earth. So it kind of lies a little bit between the moon and the Earth in terms of size, and maybe it also lies between there in terms of seismicity and how its internal structure affects that. So in order to answer these bigger questions, we dive down into some smaller measurables. So one of the things we want to do, and one of the things I'm also focused on, is what is the size and state of the Martian core? Mars doesn't have an atmosphere, or it doesn't have a magnetosphere, excuse me, in the sense that it's strong enough to protect the surface from the harsh radiation from the sun like Earth does. One of the reasons that might occur is because maybe the core isn't necessarily convecting and driving the dynamo like it is for Earth. So by measuring its size and maybe its state, we can start to answer questions on why exactly does that happen. InSight also wants to look into the crustal thickness and structure. If you've ever looked at a topographic map of Mars, you would notice that the northern hemisphere and the southern hemisphere are very different. The north is where there's a lot of volcanoes. The south is where there's a lot more craters. The south tends to have more highlands. And one of the things we might want to answer is, how far down does that crustal dichotomy extend? Does it end up affecting things that go on in the mantle? We also kind of want to use InSight to start constrain, well, why exactly does Mars have this dichotomy? We also want to answer, what is the mantle composition and structure? Is the mantle like Earth, where it's convecting as a whole? Are there plumes within the Martian mantle? Is it instead, does the upper mantle and lower mantle not really interact? We want to answer what's going on. We also want to figure out, how does heat flow out of Mars and out into the space around it? So to answer those questions, we're going to use seismology. So this is an animation courtesy of Martin Van Drell over from ETH, and it shows how seismic waves are predicted to maybe move within the Mars structure. So you'll notice that the event is going to start at the North Pole and spread out, and you're going to see P waves and S waves. And you're going to start to notice that they're going to start reflecting off the different boundary layers. So we can use these reflections in order to figure out the different internal structure layers. So how big is the core? Is there an inner core? Things of that nature. Is there a transition zone? We can also use surface waves to look at the local structure of InSight, and also use those as constraints for seismic velocities. In order to do that, we have a suite of instruments. I should also mention that InSight is a bit unique in another way. So although it is a NASA-funded mission, most of the instruments are actually built outside of the US. So SEIS, the seismometer, which actually stands for the Seismic Experiment for Internal Structure, and it's composed of a short period SP and a very broadband VBB seismometer. So it's actually built by CNES, which is the French agency, ISAE, which is another French institution, IGPG helped out, and so did the Imperial College of London. SEIS is mostly focused on considering the seismicity of Mars and also looking at the internal structure. In your photo, it's the little white dome that sits on top of the surface. And actually the white dome itself is the wind and thermal field, or WTS. So as I mentioned, Viking had this problem where most of the signal it recorded was wind driven. So for InSight, we knew that we had to put the seismometer on the ground and we had to protect it from wind. So that's where WTS comes in. And there'll be publications coming out later, and you might have heard some talks at different conferences where we're able to actually quantify how much we've improved the signal to noise ratio by covering size with WTS. Also learning from the lessons of Viking, we've included a weather station. So this will help us correlate the signals we see, so we might be able to rule out wind and other noises as opposed to internal tremors or Marsquakes. HP cubed is the heat probe. So that's what you'll see towards the bottom left. It's the other instrument that's on the surface of Mars. So its mole was designed to drill down into the Martian surface and measure how the heat moves within the crust of Mars and use that to constrain heat flow. There's also cameras aboard InSight, like any typical NASA mission. So there's the IDC, which is the instrument deployment camera, and that sits on the arm. So if you've seen those great selfies of InSight, that's the camera that's taking them. There's another camera that sits underneath the lander, the ICC. There's a magnetometer on InSight, and lastly, there's RISE. So RISE measures the spin rate and wobble of Mars by measuring InSight's location very precisely, and this would allow an additional constraint on the size and state of the core. InSight was also pretty unique in how it got to Mars. So on the left is a photo courtesy of ETH Zurich, and it's a photo of InSight being launched out of Vandenberg. So rather than being launched out of Kennedy Space Center in Florida, where most planetary missions are launched out of, it actually launched out the West Coast. So I like to joke that I was present at the launch of InSight, but I didn't actually see it because it was so foggy. I did feel it and hear it though, so it was a pretty great experience. Once it got to Mars, it used tried and true technology. So it was based off of the Phoenix lander. One of the reasons I'm playing this video is because it ended up winning NASA an Emmy for this. Can everyone still hear me? Yes? Okay, sorry. I got a warning message. So Mars does not have an atmosphere. Excuse me, it does have an atmosphere. It has a thinner atmosphere than Earth. So we can't just use a plain old parachute to drift down. That will only get us so far. So what you're seeing in the video is after the parachute slows down at InSight, it's actually going to release, and then we're going to require a different mechanism to touch down. So InSight isn't quite as big as Curiosity was, so we don't need the spy crane, which was less scary for me. I should mention this whole process took about 6 minutes. And the time between getting the signal from Mars back to Earth is 6 minutes. So this entire process was automated. So there was nothing the engineers could really do if something were to go wrong. And thankfully it didn't. But for 6 minutes, or the 6 minutes of terror, I basically did not breathe because it was quite scary. However, as you all will know, the landing was successful. So I love that image of the guy holding his breath, because that's how I imagine the majority of the team felt at the moment. I also love that handshake. But yeah, so very recently, about 2 weeks ago, InSight did receive an Emmy for its broadcast of this. And it was broadcast, you'll see in a few seconds, not just at a JPL, but there were viewing parties all across America. So you'll see Caltech there, New York City had it in Times Square. There were other viewing parties at different museums, which I really love, because the public really should become more involved with our missions and know what we're doing. So to be able to share these moments with the public, I think it helps humanize the mission as well. So once it landed, it immediately started to send photos. So the first photo is actually going to be the one on the right. The dust you'll see is those little black spots, and eventually those faded off the camera. You'll notice a rock in the bottom corner, so to speak. That's Dwayne "The Rock" Johnson. Yes, it's essentially named after the actor. The other photo, which I love, is on the left. The big orange thing that you see taking up a large portion of the screen, that's the size instrument. So that's the seismometer. So it's really great to know that not only did InSight land successfully, but the instrument landed successfully as well. One of the first things we had to do was deploy our solar arrays. So unlike Curiosity and some of the other more powerful rovers, we don't rely on radioisotopes. We can just use solar panels. So this is what Spirit and Opportunity used to rove around Mars. It's also what the Phoenix lander used, which is what InSight was based off of. So the solar panels unfolded somewhat like butterfly wings, and then they collect the power that will allow InSight's instruments to survive. The camera started taking images in and around in the InSight lander. So one of the things you'll notice is there is a rock underneath the lander, the Ace with Spades, we've kind of nicknamed it. The InSight landing, or the InSight site for landing site was chosen because we wanted somewhere that was relatively flat. Since this is a geophysical mission, we didn't have to worry about being near a certain outcrop or things of that nature. So we wanted to make it as easy as possible for the engineering team. And I say that with an asterisk. So I should have mentioned this earlier, but JPL is currently the only institution and NASA to successfully land on the surface of Mars. So it is a very difficult endeavor. Nothing is guaranteed. So for InSight, we wanted to try to make it a bit easier as possible. So that's why we chose a site that was close to the equator and was relatively smooth. But as you can see from the photos, there are still rocks on Mars. The other rock you might notice is in that final panel. And if you look really closely to the rock, you'll see that there's divots in the soil around it. Because of that, I should say, those were caused by when InSight landed, it pushed the pebble along. So it was a rolling stone, which is how it got its name. And of course, this is named after the famous rock band. And there was a celebration about this not too long ago. So again, I really do love being involved with this mission because we do a lot of things to get the media and the public involved with it. And I think having fun names for like the Rolling Stone also helped to drive public interest. One of the first findings of InSight was the presence of dust devils. So this isn't the first time we've ever seen dust devils on Mars. They've been imaged before. But what's really great about InSight is the fact that we were able to use several of our own instruments and also other NASA missions. So the short period seismometer detected vibrations, and then we were able to look at the pressure sensor and see that there was a large dip in pressure. So as the dust devil was going by, we could use polarization of the seismic sources or the seismic signals to be able to basically figure out that the dust devil was moving past InSight in a certain direction. We were then able to work with the HiRISE imager above the Mars Reconnaissance Orbiter to see images of the dust devil trails as they move past to InSight. So it's really great to not only be able to confirm your findings with your own instruments, but then able to corroborate those with other missions as well. As I mentioned, there's a weather service on Mars. So if you go on there, you can see the daily weather reports for Mars. So if you're in DC this summer like I was and it was unbearably hot, you can remind yourself just how cold it is on Mars. Or conversely, if you're in the Midwest or up in Canada or somewhere where it gets cold, you can see that the surface of Mars might actually be warmer than where you are. But yes, to get to the seismometer. So SEIS was deployed over several sols or Martian days. So the arm picked it up off of the lander deck and then placed it onto the ground. So you'll see the tether is being moved a bit. The tether was designed so that it wouldn't create any additional noise with the seismic signals that are recorded. And then in that final frame, you see the wind and thermal shield WTS being deployed over SEIS. So that all occurred in early February of this year. So since that happened, there's two main groups that have really been at work, the Marsquake service. So this is the group that detects, locates, and tries to identify and work with the other team members to figure out where these events are coming from. So it's always exciting when you get an email from them because InSight has detected something. There's also the Mars structure service. So this is the team that'll help be focused on developing that PREM-like model for the interior so that we can see a one-dimensional model of what Mars looks like. So there have been Marsquakes detected. So the panel on the left you might have seen, it was one of the first Marsquakes detected and released to the public. So what you might hear right about now is a wind noise, which generally sounds like wind on Earth, but then you're going to hear this rumbling noise, and that's the Marsquake. And then the last thing you're going to hear is it just so happened the robotic arm was moving at the same time. And I love this for outreach events because all the kids think it's like a whale or something. So it really gets them excited. But one of the important findings of this is that the Marsquake, and at least this sense on the left, resembles more of a moonquake than it does an earthquake. And this is one of the things that we're going to continue to look at over InSight's lifetime, is to figure out, is Mars closer to Earth, is it closer to the moon, or where does it fall in between those? So it's sort of a comparative seismology. In addition to that event, there was also a larger one that occurred on Sol 173. So this image is courtesy of ETH Zurich. In the top, you're going to see the low and high frequency time series, and then you'll see a spectrogram below it. So you can see how the spectra move through the time, and you can see a bit of dispersion in there. This was a really exciting event for us for a couple of reasons. So since InSight landed, there's been several events that have been detected. So what you're seeing here is how the noise changes on Mars. So the more purple you see, the quieter it is, and that represents the night essentially. The more yellow you see, it's noisier. So that tends to be when the wind is more active. So a lot of the events we've detected tend to be on the night side, which makes sense because it's quieter, so it's easier to detect them. But that large event that you saw on the previous panel is the green star there, and it was recorded during a relatively quiet time. And as InSight moves forward, we want to be able to use these events to start constraining the seismicity of Mars. So again, this goes back to how active is it compared to the moon or compared to the Earth? Where does it fall sort of on that spectra? And already we've been able to rule out some previous models. So we know that it's probably more active than the moon, but it's going to be less active than Earth because essentially Mars doesn't have plate tectonics, so it doesn't have that driver. If you are really interested in seeing the seismic data available for InSight, you can use the IRIS tools. So there is a brief period of embargo, but that only applies to the seismic data. So if you want the raw images, they're going to be on the InSight NASA page, essentially immediately, as well as the Mars Weather Service. You can use the IRIS DMC or Data Management Center to download the events. So as of right now, you'll be able to get raw and calibrated data up through the end of March, but in just a few short, essentially a week or so, you'll be able to get data up until the 30th of June. And then every 3 months, there'll be another 3 months released. So one important thing you might want to consider is the frequency of the data. InSight does record over several frequencies, but because of data limitations sending it back, it won't always send the high frequency data. That tends to be only available for events that are detected or things of that nature. So if you try to download, say, the 100 hertz data, you might notice that it's not available every single day, and that's the reason why. So if you're really interested in keeping up with InSight and knowing what's going on, I highly recommend following them on Twitter. The NASA social team did a really great job of figuring out what InSight's personality should be. So Curiosity has a very go-getter attitude because it's roving around Mars, it's drilling, it's hitting things with lasers. InSight is more chill. It sits there and waits for the science to come to it. So for that reason, they made it more of a Zen rover. When it placed the seismometer on the ground, it had a great tweet about being centered and balanced in life. So if you're ever having a rough day, I would recommend checking it out because it tends to be very like Zen and passive and calming. InSight's also on additional social media, including Facebook, Instagram, and we'll be presenting at additional science meetings. So actually today there was an InSight meeting at the Geological Society of America being held in Phoenix. Later next month, there'll be the Sage Gauge where there'll also be a presentation on InSight, and then there'll be a full session at the AGU Fall meeting in San Francisco in December. So keep an eye out for all those exciting info. So now I want to talk to maybe the future. So InSight, at least I hope that we can convince NASA that the seismometer is a very crucial instrument. So as we head back to the moon, hopefully seismometers will follow. So NASA has a plan, Artemis, to return humans to the moon by 2024. It also has a commercial lunar payload service, CLIPS, in which commercial companies will build landers to take science instruments to the moon. And of course, we're not the only country that's interested in planetary exploration. So just last month, the Indian Space Agency launched an orbiter and a lander. Unfortunately, the lander had a bit of a hard landing, which is really difficult and hard for the team. It did have a seismometer on it, which would have been great to have more seismic experiments on the moon. But space travel is really difficult. Nothing is ever guaranteed. In addition to India, there was an Israeli company, Marusiak, who also attempted a landing on the moon. China has been a bit more successful. So their Chang'e program had successfully landed on the moon almost a year ago. And its program will continue. And I believe its next one will also have a radar instrument on it. So it can also start to look at the near surface but internal structure of the moon. In addition to our moon, there's also interest in maybe going out to the outer planets with seismometers. A lot of these icy ocean worlds could be habitable. They're called icy ocean worlds because they have thick ice shells with subsurface oceans lying beneath them. These bodies, in some cases, tend to not have a lot of craters, which might indicate that they're young, and if so, maybe they're active, which would be great to send a seismometer to, because the seismometer would be able to figure out how thick the ice shell is, and how far you would have to drill to hit that subsurface ocean and maybe look for life in that sense. We also could be able to constrain how seismically active they are, and maybe what sort of tectonic regime they exist in. So because of this, there was the proposed Europa lander. This was designed to be a follow-up to the Europa Clipper mission, which is currently being built. If the lander was to be funded and to go, it might contain a seismometer, which would help figure out how thick the ice shell of Europa is and how seismically active it is. What was also funded is the Dragonfly mission. So this is being built by the Johns Hopkins Applied Physics Lab in Laurel, Maryland. I nerd out about this because I just think this mission is amazingly cool. It's not just going to land on Titan, which is the largest moon of Saturn, but it's going to fly around Titan. So it's essentially a quadcopter. It can cover several hundred kilometers and be able to image the methane and hydrocarbon lakes of Titan. It can sample the surface, measure composition, make atmospheric and surface observations. But also really exciting is it will have a seismic component to it as well. So we can start to look at seismicity in the outer solar system. So just to sort of wrap up here, what I really want to hammer in is seismometers are the preeminent method if you want to figure out what's going on inside of a planet. So if you want to know what could control these surface conditions, you need to look within the planet. So for that reason, the Apollo missions were really successful. InSight, I think, is also going to be very successful. And then I hope its legacy can be that we need to send seismometers back to the moon and also out into the outer solar system to continue on with seismic exploration. So with that, I just want to acknowledge the InSight team, in particular the PI, Bruce Banner out of JPL, and his deputy PI, Sue, the SEIS investigator, Philippe Longonnier, as well as some other scientists that have helped me, and in general, the InSight team I want to thank. So with that, I'll take any questions.
Thank you so much, Angela. I really appreciated that you gave such a great overview of everything that's going on with the InSight mission. If you do have any questions, please enter them into the questions chat box that you should see on your webinar control panel. That's where I'll be taking and listing questions. So I see that some are coming in. I'm probably going to butcher your last name, so please forgive me. Have grace. Lisa La Dilame asks, is fiber optic based seismology being considered for instrumentation?
I know it's being researched at various institutions, but as far as I know right now, there's no mission that has the fiber optics. They certainly are very compelling. I would like to see them because I think they might be good for maybe, say, rover missions. But yeah, that is definitely something that I think NASA should look to in the future, is developing not just these sort of standard seismic instruments that we're used to on Earth, but also expanding them to some of the new avenues and making sure that the instruments we're sending are state of the art.
Great, thank you. Tom Perkins asks, does Mars have a liquid core?
It does, as far as we know. So we're able to constrain that for a few reasons. So we can use moment of inertia to figure out roughly the internal structure layers. So I should mention that right now the core of Mars is constrained to about 100 to 200 kilometers in size. So InSight is really designed to narrow it down. So we can use mineral physics modeling to figure out at the depths of that core or core mantle boundary, is it more likely to be liquid or solid? So from various investigations, we anticipate that yes, the core of Mars is liquid, and there's a chance there could be a solid inner core, but really we need to get some big events that can really see deep down into Mars to be able to answer that question.
Yeah, this is a great follow-on question from another asker who just asks, according to the present data, could you estimate the thickness of the Martian crust?
The team is currently working on that. And I don't want to jump the gun and answer that with a numerical answer, but stay tuned for coming publications and presentations. But there's different methods we can use to start assessing and to get a rough idea.
Great. Again, if you have any more questions, you can please feel free to send them in. Here, let me organize this a little bit, Angela. John Townend asks, how long is InSight designed to continue operating? What factors control that?
Well, that's a great question. So the nominal mission is 2 Earth years or 1 Martian year. So we're roughly a quarter of the way through that. So InSight landed on Cyber Monday of last year in 2018. So that's the Monday after Thanksgiving. So it should go about 2 years from that. However, a lot of NASA missions do tend to get funding beyond their nominal mission time. So I'm hoping that's the case with InSight. Probably the biggest factor will come down to the solar panels. So if you have followed the Mars Explorer missions, Spirit and Opportunity, they were designed to only last 90 days, and they ended up lasting years because their solar panels work so well. So that's probably the limiting factor. With the Apollo missions, their limiting factor was just funding. So it got to a point where the instruments themselves worked, but there wasn't enough funding to continue to download the data and analyze it. So that's why those missions had ceased.
Great. Andrew L, I'm not going to try your last name, asks, is there any planning for seismic penetrators?
Oh, I think I know what you mean. So if he means like a penetrator that has a seismometer like on the tip or something, that's been proposed. So I know with the Japanese Space Agency, they were that was one of the proposed ideas for lunar exploration. So as I mentioned, there is a mega regolith on the moon. So an idea is that if you get a seismometer buried within it, you might help reduce some of those scattering effects. So yeah, this is definitely like an idea that's been thought of, but as far as I know, it has yet to be implemented.
Okay, sounds good. And yes, he did comment back that yeah, what he meant was like dropped from orbit.
Yeah. Yeah, I've been asked that before. Why don't we just like drop seismometers from planes? Like they are fragile, so you have to keep that in mind.
Right.
I love the idea of like, yeah, just dropping them from orbit so you get good global coverage, but yeah, you need to figure out how they survive the landing.
Yeah. But currently, I mean, I know that the seismometer, is it buried at all or no? I mean, I know it has the vacuum cover, but is it just sitting on the surface? Or
Yeah,
is
so
it?
it sits on the surface.
Okay.
It's not subsurface.
Okay, got it. Thank you. Ross Catone asks, has the analysis team been able to say anything about the mineral composition of Mars?
I'm gonna defer that to say that I would wait for coming publications. But so the current estimates that we have for the mineralogy of Mars, there have been Martian meteorites that have landed on Earth, so we're able to get chemical composition from those. And then we do have the rovers along the surface so that they can also get a sense of like, what do the surface rocks look like, and we can use mineral physics modeling to see what that might look like at depth. So that's the current published idea of what's inside Mars compositional wise. Those are where those constraints mostly come from. And also, again, with gravity constraints and moment of inertia and things of that nature.
Great, thanks. Sunny Park asks, could you comment on the current status of the heat probe?
I was wondering if someone was going to ask about that. Yes. So I had this image in case someone asked. So the heat probe, for those that maybe aren't up to speed with its status, was designed to drill down into the Martian surface. However, after its first day of drilling, it only made it down about 14 inches or so. So what you're seeing in this image here is the probe is sticking out of the soil. So ideally, the chassis should have been sitting over top of it to tap it down. What ended up happening is the top layer of the surface is not as cohesive as we were expecting. So you can kind of imagine it if you were having like a tray of maybe flour or something, or sand at the beach, and you're trying to dig down, and it just kind of, you don't really get anywhere. So the InSight team is currently working on different ways that we could get the mole to continue to go down into the surface. So hope is not lost. We're still working on the problem. So hopefully we can figure out a solution. But currently the image that you see here is essentially its current status on Mars.
Great, thank you. Let me see. Patrick Matulka asks, how long would the Dragonfly mission remain at each location in order to maximize its chances of detecting seismic signals at various locations on Titan?
I do not know the answer to that question. I'm not a member of the Dragonfly team, so I'm not at liberty to, or I don't have access to that sort of information.
Sure.
So yeah, I honestly don't know. Sorry.
Yeah. No, it's okay. I think that's totally fine. Sunny Park asks, could you explain what are calibrated and derived data as opposed to raw data?
So the raw data that you can download should basically be what InSight sends back before we do any sort of analysis on it. To be honest, I'm not 100% sure what are all the processes that go into the final calibrated data. There are several papers that will give you better detail than I would risk telling you and accidentally telling you the wrong thing. So I would refer you to those. Sorry that I can't be more specific about that.
Yeah, I mean, you mentioned these papers. I mean, I'm not.
Oh, yes, sorry.
Which papers are those?
There's Science Reviews has a whole series of InSight papers.
Okay.
And there's specifically one that Philippe Langogne, the PI of InSight, wrote that details all the specifications of the size instrument. So if you're really interested in all the little details into how size works, that paper has basically everything that you would want to know on it.
Yeah.
And I think if you're looking specifically for the calibrated data, there should be a paper that talks about exactly what goes on. I think it might also be available on the IRIS website. Sorry about that.
No, I mean, I don't know either. So, but I'm in headquarters, not at the data management center. So I honestly don't know either. Andrew L also asks, you talked about InSight as a whole and what the current expectation is for InSight for its lifetime. But this question asks specifically, what is the current expectation for the lifetime for the size operation?
Well, you can't really separate size without separating InSight.
Okay.
So yeah, it's not like we would, I can't, well, I guess I shouldn't speak to NASA's plans, but I can't imagine they would fund the seismometer to keep or no, I shouldn't say that. The size instrument would have the same lifetime expectations as InSight in general. So it's
Yeah.
funded for 2 years, and if NASA deems that it's worth continuing to fund in the future, then it will keep going until essentially, yeah, the power would run out or the funding runs out.
Angela, what are the costs in its current operation? I mean, sure, it takes a lot to build, it takes a lot to get to Mars, but what are the current, operational costs, if you know any of that? Like, in that scope, I mean, are they minimal compared to, actually getting the instrumentation built and sent, or, um, what do those?
Um, I honestly don't know. I would
Okay.
imagine so,
Yeah.
but I honestly I don't know.
Yeah, sure.
I'm a poor grad student, so those types of large
I
amounts
know,
of money.
right? We were talking earlier about the Discovery missions and those costs, right? It's like, oh my gosh, those are astronomical,
Yeah, it's crazy.
and
We're
those
like,
are just
oh, it's a low cost mission. It's only a few 100 million. But
brilliant,
then, like,
right?
when you think of the cost of like
Right,
frontiers or flagship missions that are billions, yeah, it
right,
kind of have to
exactly,
change your frame of thinking.
exactly. Okay, so Ratish asks, is that a basalt on the Martian surface shown in the slide? Early operations, in quotes.
Um, the rock, I think, is what he means.
Yeah, yeah, this
I
one
would
I
guess so, but I should also say, like, I am a seismologist, not a geologist.
right.
So don't quote me on that.
Right, right, of course. Yeah, me too. It's like black rock, gray rock. So,
Yeah. There will be papers coming out later this year, and one of them is focusing on the geology of Mars at the InSight landing site, and that will definitely discuss all the different features you see and what we think they are.
perfect. So,
Yeah,
what is
so those
I?
will be coming out in a few months, I should say. Sorry.
Yeah, you've been talking a lot about publications that are coming out. Where should we expect to see those, and what type of time frame?
Um, there'll be an there'll be a couple of different. So there'll be some in high impact journals. So
Mm-hmm.
some are being submitted now, so they should be coming out in a few months. And then as the mission progresses, we'll obviously keep publications going. So we're not going to wait for the entire mission to be over before, say, releasing the catalog of events. That will be updated as the mission progresses. Um, I would say the best chance, if you can attend any of these meetings, those
Mm-hmm.
are really where you'll be getting a lot of new information. So if you happen to be at GSA, there was a great session this morning. If you're planning on going to AGU's fall meeting, there'll be a whole session there in addition to posters and things like that. Um, and there you'll be able to speak with a specific scientist whose expertise um, lies in identifying those rocks and such. Again, I apologize for not giving you a straight answer. I just don't want to misspeak.
Yeah, no, that's totally fine. So, and we just got a couple of comments through from Bill Harbert and Taylor Washington that just wanted to say thank you for the webinar and that it was a fantastic talk and that it was really interesting. So I just wanted to make sure that you knew about those. And then Tom Perkins asked, what is the main cause of the Marsquakes that InSight picks up? Is there more than one mechanism to generate them?
Okay. So in general, we expect seismicity to come from several sources. So one could be impacts. InSight is closer to the asteroid belt, and it might pick up more impacts. Also, because it has a thinner atmosphere than Earth, they won't disintegrate in our atmosphere like how we have bolides and such. So we expect that impacts could be one seismic source. Like the moon, there could be contractional cooling. So those would also generate larger tectonic events. There's also mass wasting on Mars. So avalanches, landslides, things of those nature, InSight might be able to pick up. So those are different seismic sources that we might look for. If there is groundwater, there could be, as it freezes and expands, that could also generate some small seismic sources, if that exists, of course. So uh, there's a lot of different things that they could come from. But if you're asking me specifically what generated the quakes that we saw, that I'm going to have to say is unfortunately embargoed. So I can't discuss that.
Great, thank you. Thank you so much, Angela, for your talk today, and I appreciate the really engaging Q&A session as well. With that, I'm going to go ahead and say thank you, and yeah, there's just a lot of good comments coming in. Angela, just that it was very informative and interesting, and thanks for your time. And so thank you everyone for your active participation in the webinar, and thank you so much for your questions. And Angela, of course, thank you so much for your presentation. I think it really
Thank
gave,
you for having me.
yeah, I think it gave a really good overview of what InSight is and what we're expecting out of it, and all the exciting science that's about to come out. So it's all really encouraging and exciting. So thank you
Yep,
so much.
stay tuned for more.
Yeah. All right. Take care. Have a good day, everybody, and stay tuned for the next IRIS webinar, which will be at the end of October, by Elizabeth Vanacore from the University of Puerto Rico. She'll be talking about the Caribbean Seismic Network, and they just had a magnitude 6 there, so there should be a lot to talk about. So, all right. Thank you, everybody. Bye.